probability isn't always fixed. Sometimes you learn something new, and the moment you do, the probability changes. That's the entire idea behind conditional probability. It's the mathematics of updating your belief when you receive new information. The word conditional sounds complicated, but it isn't. It simply means given some condition. Or more naturally, after learning something new. Without any new information, you have one probability. After learning something, you have another. Conditional probability is simply the probability after new information arrives. Let's start with a familiar question. What's the probability of drawing a king from a standard deck? 4 kings, 52 cards, that's 4 over 52, or 1 over 13. Now let's change one thing. Given that the card is red, what's the probability it's a king? We learned the card is red. That information changes everything. We're no longer choosing from 52 cards. We're choosing from only 26. And among those, there are only 2 kings. 2 over 26, or 1 over 13. The condition changed the sample space. Here's the intuition. Originally, every card was possible. But once we learn the card is red, the black cards are impossible. They no longer belong to our sample space. Conditional probability doesn't change reality. It changes what outcomes are still possible. Every time new information arrives, your sample space becomes smaller. Imagine choosing a student at random from a class of 20. Now suppose someone tells you the student wears glasses. Immediately, you're no longer looking at all 20 students. You're only looking at the 12 students wearing glasses. Once again, the sample space shrinks, and so does the probability calculation. Don't worry, we're not going to memorize a formula today. First, you need the intuition. Conditional probability always asks the same question. What is the probability of an event, given that something else has already happened? Once you understand that idea, the formula becomes almost obvious. What does this strange symbol mean? What does the vertical line represent? We'll build that notation and the complete formula next. This tiny symbol confuses almost everyone. That vertical line is not division. It simply means given. So instead of reading P of a bar B, read it like this. Probability of A, given B, that's all it means. The probability of A, after we've learned that B is true. Now let's think visually. Suppose someone tells us that B has already happened. Immediately, everything outside B becomes impossible. Inside this smaller world, what are we trying to find? We're asking, how much of B also belongs to A? The answer is the overlap. That's why conditional probability is really just asking, what fraction of B belongs to A? The formula simply says, take the probability of both A and B happening together and divide it by the probability of B nothing mysterious. Let's solve one. A standard deck has 12 face cards, 4 jacks, 4 queens, 4 kings. Now someone tells us the card is definitely a face card. Our sample space immediately shrinks. We're no longer looking at 52 cards. We're only looking at 12. Kings equal 4. Face cards equal 12. 4 over 12 equals 1/3. So the probability becomes 1/3, not because the deck changed, but because our information changed. Conditional probability appears everywhere. A weather forecast changes after new satellite data arrives. Doctors update diagnoses after receiving test results. Spam filters update their confidence after seeing certain words. Every time new evidence appears, the probability changes. Conditional probability gives us the mathematics to describe that update. Machine learning uses conditional probability constantly. Imagine an email classifier. Before reading the email, the chance it's spam might be fairly small. Then it sees the words, free, lottery, claim now. Each new piece of information updates the probability. This simple idea eventually leads to one of the most famous machine learning algorithms, naive Bayes. And that's where conditional probability becomes incredibly powerful. Let's summarize. Conditional means given new information. New information shrinks the sample space. We only look inside the condition. The overlap tells us what satisfies both events. Probabilities change when information changes. A deck of cards is known to contain only red cards. What's the probability of drawing a heart? 13 over 26, or 1/2. True or false? Conditional probability always uses the original sample space. False. It uses the updated sample space. The probability of rain changes after receiving new weather data. Which concept explains this? Conditional probability. Remember this sentence. Conditional probability doesn't change reality, it changes what you know. But here's the twist. What if we want to reverse the question? Instead of asking the probability of a given B, we ask the probability of B given A. That simple reversal leads to one of the most famous equations in statistics, Bayes' theorem. And it's one of the foundations of modern AI. We'll uncover it next time.